Hello, my name is T. Srinivas, Associate Professor in the ECE Department, Indian Institute of Science. This course is called the Photonic Integrated Circuits. So, this is a brief outline of the course. The first lecture is on the overview of photonic integrated circuits. So, we will start with what is meant by photonics, what are photonic devices, various types of devices like the passive devices, the functional devices, the active devices, and we will look at some applications, and also if possible we will try to do some new developments in this subject in this overview lecture. Photonics can be considered as analogous to electronics. In electronics, as you know, the fundamental particles of nature, the electrons take the prominent role. All the devices that you see around like the laptops, the computers and the TV are all electronic devices, because the electrons flowing in the wires or semiconductor devices are the ones which take the main functionality. In comparison, we can say that photonics is a subject involving light particles. So, you can say take photonics as analogous to electronics. I have put a few information operations that we usually do with electrons. As you know, we can generate signals, we can control the electronic signals, you can transmit from one point to the other, you can process, we do a lot of signal processing, and finally we may have to display all this information. So, all these operations we do with electrical signals and electronics in the conventional technology, and it is possible to do most of these functions with light. That is the subject of photonics. So, if you go to the fundamentals, as you know, the electronics involves the Fermi-Dirac statistics. In semiconductors you use Fermi-Dirac statistics to study the properties of the materials, and as you know, the electrons are massive, they have a certain charge and so on. These are the fundamental properties. In contrast, you have photons have zero rest mass and no charge, and you use Bose-Einstein statistics to study these properties. So, what are the advantages or why photonics is becoming important in the present day world? The demonstration is already there. For example, all the transmission is taken over by photonics now. So, in future you can expect that many of the functions that we do with electronics will be taken over by photonics. The photonic integrated circuits or integrated optics can be considered as analogous to electronic integrated circuits. In olden days we used PCBs, then the breadboards etc. to build electronic systems. So, now we have all these systems onto a chip. So, you can say that integrated optics is analogous to integrated electronics, where the main aim is to create various optical components necessary for a given system on a single substrate. So, there are several examples in use today like N by N switch matrices, and chip for the fiber optic gyroscope, and even a micro optical bench where all the optical components were built on a single silicon wafer. I would like to take the example of an modulator, optical modulator on a lithium niobate chip. This is a typical example and is a commercial device today. It is based on the electro-optic effect or the Pockels effect, that is a change in the refractive index of the medium with the applied electric field. The picture shows the top view of the lithium niobate optical modulator. You observe a branching circuit, the double lines that you see are waveguides, and light can be propagated through these waveguides, and you also see a branch. This is a Y branch where the light could be divided into two parts, and there are two electrodes where you can apply the electrical signal, and light could be affected by these electrical signals due to the electro-optic effect, and finally it is combined back at the output combiner, giving us the modulated light output. The modulation happens with the change in the refractive index. The electro-optic effect, as I said, implies the change in the refractive index due to the applied electric field. As you know, the light propagation can be described by e power I omega t minus beta z, and when you apply voltage to these electrodes, you can say that the propagation constant of the light propagating in these waveguides changes and effectively phase modulating the light that is propagating through that. So, you can expect at the output a modulated light. So, this can be used for very high speed modulation of the orders of 10 gigabits per second or more. So, there are many other improved properties, like the performance is very good in terms of the voltage required, the bandwidth and chirp characteristics and so on. Just to compare, if you would like to do this directly with a semiconductor laser diode, you need to manipulate the modulating injection current of the laser diode. So, it is not advisable to, it is not preferable to disturb the properties of the semiconductor laser diode. So, for high speed operations, it is very preferable to use an external modulator like this. This is a typical example of an integrated optical modulator. Another example is the directional coupler, where you have two waveguides very close together. These are the two waveguides very close together, and this could be fabricated by standard lithographic process. Once again, we use the electro-optic effect, where there are two electrodes placed on the waveguides, and the light propagating in one waveguide could be affected by the light, affected by the presence of the other waveguide. For example, you can design such that the light propagating in the first optical waveguide could be transferred entirely to the second or the fourth output port, creating what can be called as a crossover state. Similarly, if there are two signals S1 and S2, so these could be exchanged to S3 and S4. So, S2 can go to S3 and S1 can go to S4, creating the crossover state. And by applying voltages, we can effectively change the refractive index, so that the light from the port 1 can go back to the S3 and light from S2 can retrace back to S4. So, this is a basic function of an optical switch. When there is voltage, it is in the bar state. When there is no voltage on the electrodes, it can be in the crossover state. So, I am showing you a few parameters of fabricating this device. Typically, the lengths are of the orders of a few millimeters, and the waveguide widths are of the orders of a few microns, and the spacing also of the orders of a few microns, 4 microns typically. And we process this by diffusing titanium into the lithium niobate at 1000 degrees centigrade for about 9 hours. So, typical thickness of the titanium film also are of the orders of a few angstroms. So, this is another example of an integrated optical device. So, there are several features of photonic integrated circuits. The most important one being the single mode operation. All the waveguides are designed such that they operate in single mode. So, this is incompatible with the fiber optics, where you use single mode optical waveguides. Alignment is an important problem in optics, which can be solved by proper packaging, and these devices can withstand vibrations, and you can also manage the temperature changes and so on. This is one of the greatest advantages of using photonic integrated circuits rather than discrete components. It is also possible to control the wave guidance. As you know, in free space or in fiber optics, it is almost impossible to control the propagation of light, particularly for example in the networks or in switches. If you want to change the direction of the path, or as we saw earlier, modulating characteristics, it is not possible to do in a free space or in a controlled environment. It is possible to do in photonic integrated circuits in a very easy manner, as we will see as we go along. So, another important advantage is, compared to the bulk devices, is low operating voltages and short interaction lengths. These are because of the wavelengths involved and the dimensions of the devices are very small. So, for example, the spacing between the waveguides is very small, so you can have very low voltages for control operations. And also faster operation is also possible due to the small spacing between the electrodes and less capacitive effects. The power density of light propagating these waveguides is very large. So, you can expect many nonlinear effects which can be used effectively in photonic integrated circuits. Of course, like in VLSI circuits, these are very small, so they are very compact and lightweight, they consume less power, they can be used, batch production can be used to fabricate devices and so on. These are the generic advantages of going for miniaturization and batch production in photonic integrated circuits. So, historically we can say that during 1960s, just after the invention of the laser, most of these technologies have developed. In particular, the work on optical waveguide theory had historically they have been done during 1960s. Then you can say that during 1970s is the era of optoelectronic devices, where all these principles were translated onto semiconductor devices, creating many new devices like very miniaturized lasers and optoelectronic modulators and so on. So, you can say that in 1980s is the era of implementation leading to launching of subsystems and many applications. During 90s we can say is the development of WDM. Networking is an important development during 90s, requiring a lot of devices for networking applications. So, now we can say that all optical components is the order of the day, where we try to do as many functions as possible on a single chip. This is a brief history, but find that there are a lot of intricate developments that you can see in the references given at the end. So, let us start the talk with optical waveguides, which are the basic interconnection elements in integrated optics. Like wires in electronics, you can say that optical waveguides are the basic elements interconnecting various components on the chip. Then the waveguides can be used for making many passive devices, passive waveguide components you call, like branches, tapers, couplers and so on and so forth. And as we saw earlier with the electro-optic effect, lot of dynamic effects can be used to control the properties of these devices on waveguides. So, the dynamic effects include the thermo-optic effect, the electro-optic effect, the acousto-optic effect, the magneto-optic effect and many nonlinear optical effects. So, typical devices are the modulators, switches, polarizers and so on. Of course, there are a lot of optoelectronic effects where electrons play an important role. We can control the properties of the materials by changing the electronic properties. The optical properties can be changed with electronic properties of the device and the materials. And finally, of course, the technology is the most important element in the development of this technology. We need to consider the various materials and fabrication technologies involved in fabricating these devices. So, these are the typical optical waveguides that we come across in integrated optics. These are all the cross sections I am showing you. The first one is the buried type of optical waveguide. Then the next one is the ridge waveguide, where you can deposit a material on a substrate and etch out unwanted regions. And then you have the loaded type of waveguides, where you can load another material on top of a slab type of waveguide and change its properties. And you can also use other materials to load these waveguides. And finally, I am showing you voltage induced type of waveguides, where as we have seen earlier, you can use electro-optic effect or some other effect to change the refractive index. So, what is shown here is a substrate with a slab waveguide, and top of this you have a electrode placed, and by applying voltages you can induce the waveguide. So, this is a brief review of technology that is used in the fabrication of these devices. I am showing the various waveguide materials like polymers, glass, crystals, then of course the silicon and the magnetic materials and so on and so forth. So, there are several fabrication techniques based on the materials chosen, you have deposition techniques like the spin coating, the vacuum, evaporation, RF and DC sputtering, chemical vapor deposition methods, polymerization and so on. And you also have diffusion techniques, ion exchange process. Then for semiconductors you have epitaxial growth techniques like liquid phase and vapor phase epitaxial growths and so on. So, the circles indicate the importance or the level of development of the technology. The double circles imply that it is much more effective and more utilized. Now, let us go into some passive devices like power dividers, the polarizers, the multiplexers and demultiplexers, gratings, lenses, all these based on the optical waveguides. So, the generic name given to many of these is the planar light wave circuits. So, there are some examples of the power dividers. You observe that there is a single waveguide at the input which is branched into several waveguides at the output. There are several interesting features of these devices that you can observe, that as the light propagates into the waveguides, as you know, in terms of its modes, we will get to this mode theory later on, but the light, we can say that the light propagates in terms of modes, and the modes characteristics are dependent on the size of the waveguide, in particular the width of the waveguide. So, the top view of these power dividers show one input port and several output ports. The first one is a symmetric 2 branch power divider where you have a straight waveguide and a tapered region to taper out the input mode into 2 output modes, and there is a junction which is also interesting case here. And finally, the output waveguide widths are also chosen such that they are all once again single mode. And another important feature is that the angles involved, in order that the losses of the power dividers are very less, we need to choose the angles very small, as we will discuss later on in the course. Similarly, the second device that is showing asymmetric 2 branch consists of a bus waveguide from which the power can be tapped out into the output port. So, this is an asymmetric compared to the previous one. You can also think of a symmetric 3 branch waveguide where you have a input bus waveguide and 3 output ports. Of course, this is not symmetric, the output distribution is not symmetric, but depends on many factors including the placement and the tapering portion and so on and so forth. So, we can create higher order branches from using 1/2 waveguide branches. For example, here it is shown that you can make a 1/4 branching waveguide power divider using 3 1/2 power dividers. In the beginning we have seen a directional coupler where light could be exchanged from the input port to the any of the output ports, but even though there is a higher refractive index region in the waveguides and lower refractive index region in the intervening medium. So, we saw that the light could be tunneled from input port to the opposite port. So, directional couplers are very useful for many applications for switching the power between different ports or redistribution and so on. A directional coupler is typically considered as a multi-purpose device which can be configured for many purposes. In particular, in association with other electro-optic effect and so on, we can say that is a multi-purpose device. The second picture shows the 2 mode waveguide coupler where in the intervening region there can be 2 modes of this waveguide and there can be interrelationship between them leading to some redistribution of the power at the output ports. And it is also possible to use the coupler in the backward propagating mode also. That means power injected into the port 1 is redistributed across all the 3 remaining ports, but many important applications. Typically, to extend in the part C, in the figure C, we have a 3 waveguide directional coupler where light could be exchanged between 3 waveguides in the intervening region. For example, the power at the input port could be redistributed across 2 output ports, or if the middle port is extended, it could be distributed across the output port also, not exactly equally across all these, but could be calculated and arrived at what is the ratio of the power across each of the output ports. Star couplers are very important devices in many applications like in WDM systems where you need to distribute the power across many users. So, in here in the part A I am showing a transmission type of star coupler where light is injected into one of the ports and is redistributed across the output ports. The important feature of this star coupler is the mixing region where the light injected into the input port can get mixed up and redistributed across the output ports. It is very difficult to analyze the operation of this except in some very crude manner. The second one shows a reflecting type of star coupler where the light input from one of the ports is reflected at the reflecting mirror and then redistributed across the output ports, including the port that from which the light came in. So, these regions are called the mode mixing regions and could be analyzed by using geometrical methods to find out how much power comes out of each of the output ports. You can easily expect that the power distribution is not uniform and is an important challenge for the designer of star couplers. Polarizers are important devices in optics because light has got different polarizations. In fact, you have all the 6 components of the electromagnetic field to be manipulated and controlled. So, in order to build polarizers you need to choose materials which have got anisotropic properties where the refractive index of the material changes in different directions. So, here is shown glass waveguide based the figure A shows the glass waveguide based polarizer on top of which you coat a anisotropic medium like calcite. So, what is shown here is a waveguide in the glass which is controlled by the loading anisotropic waveguide at the top. Based on the axis chosen of the anisotropic crystal you can choose one of the polarizations. There are 2 polarizations at the input TE and TM and you can choose one of them based on the polarization based on the orientation of the crystal that you choose. Similarly, the second one shows a polarizer on lithium niobate. The substrate itself is anisotropic and it can support based on the design both the polarizations, but you can coat a niobium oxide film on top of that and change the properties to get only a TE polarized light output as shown in the figure. So, multiplexers and demultiplexers are necessary in all communication applications. So, the important requirement here is the input optical fiber brings in light from different channels. Let us say the channels are at the wavelengths lambda 1, lambda 2, lambda 3 and lambda 4 which carry independently modulated light signals, and the requirement is that they have to be separated out at the output port. These are the output ports. The requirement is that first port should tap one channel, second port should have a second channel and so on. So, all the 4 can be demultiplexed at the output ports by using the waveguide elements, and in this particular case I am using gratings. These 3 are gratings designed to tap different wavelengths. So, the first grating will deflect the light into the first output port and all the other 3 wavelengths are passed unaffected, and the second grating will deflect the light into the second port and so on. So, it is possible to design a device like this called a transmission grating filter to demultiplex all the signals. The other one, the example B shows the reflection type of grating where the input light is reflected across different output ports rather than transmitted. So, all these are based on the slab waveguides. As you see here, the basic substrate is chosen, a slab waveguide is made, and according to the requirement channel waveguides are induced and gratings are used to deflect the light across these ports. So, lenses are also an important element in optics. In the conventional integrated optics, people have tried to imitate whatever is there in the bulk optics onto integrated optics. Lenses are one of the important components which can be used for converging and diverging signals and imaging and so on and so forth. The figure A shows a gradient index type of Fresnel lens where the refractive index gradually varies across the length, across the width. So, there is a maximum refractive index in the middle and gradually reducing refractive index outside and according to particular given pattern. So, you can say that there is a refractive index pattern or a profile across the width of the waveguide which can be designed to make a converging type of lens. So, the input wave is shown as a broad wave spread across the width of the lens and focusing at one particular point. So, we can contrast this with the conventional bulk lenses where you have a 3-dimensional spread of the wave. Here the wave is spread across only the width of the lens and is being converged at a given point. So, we can also think of a gradient thickness type of lenses where the thickness is varying across the width and the refractive index being same, and it can also converge the light to a particular point. So, gratings are have many functions in many applications in optics and integrated optics. I am showing you some applications. The gratings can be used as an input output coupler. This is one of the important applications presently. One of the important problems I can mention in integrated optics is a coupling light from input optical fibers onto the chip, and gratings do a very good job in this connection. So, here we have in the figure A we have a grating printed on the chip, and light is launched from outside onto the chip. So, the grating could direct all the light that is input onto this into the chip very efficiently. So, there are many other applications. I could mention that this mode converter, if you have 2 or 3 modes, you can convert between the modes or select some particular modes using these gratings. So, typically a grating is formed on the waveguide and light is passed through that and the mode could be converted. So, another application is a wavelength filter. When you have several wavelengths coming in, the grating can choose a given wavelength like lambda 2 is shown here, and all other wavelengths are rejected. It can be the opposite also, like all the wavelengths are passed through the grating except the one which matches with the grating pitch. So, you can have a wavelength filters based on the gratings. So, this is a typical commercial application that is available called arrayed waveguide grating. This is available on a silicon wafer, and I am showing a schematic of this. The functionality, first let me describe the functionality. There are several input waveguides and there are several output waveguides to handle, and light could be passed through any of the input waveguides through an optical fiber, and all the entire thing what is shown here is on the chip. There are 3 regions. One is the input region, then you have the slab regions, mixing slab regions, and there are variable length waveguides. So, the operation is like this. First of all, the light is mixed up in the region and redistributed across all the inputs of the waveguides, and the waveguide lengths are unequal, creating different phase shift across the output of the waveguides. So, the light coming across the first port has the least delay, and the one which is coming out of the outer port has the maximum delay, and it could be designed, the lengths could be designed such that the phase shifts across each of these when combined at the output port could lead to superposition only at one port for a given wavelength. So, it is possible to focus each of these wavelengths that are coming from the input port at different output ports using such a structure. This is analogous to antenna arrays, some of you must be familiar with, where if you give a progressive phase shift to each of the antenna elements, you can beamform in one particular direction. Similarly, by giving a progressive time delay across each of these waveguide elements, we can form the beam at any given output port. So, there are many variations of this in practice to optimize the chip size and to reduce the properties and so on and so forth. So, let us get into some dynamic devices where you can control the properties or the function of the device by using many of these effects. We have thermo-optic effect where you can use the heating of the device. You have already seen the electro-optic effect where you can change the refractive index by applying electric fields. You can also have what is called the acousto-optic effect where you can induce refractive index changes by using a strain or sound Similarly, magneto-optic effect involves using magnetic fields to change the material properties, optical properties of the material, and finally you can also use an external optical signal to change the properties of the light that is propagating in this. So, nonlinear effects should be studied especially where a lot of interesting properties for many applications exist by the light that is propagating inside the waveguide itself. So, this is a typical thermo-optic device. On a glass substrate you see an interferometer that we saw earlier, and typically a 4 micron width, and the light could be launched through this input port, and these are the two heating elements of the typical size of a 6 microns. When you apply voltage across these heater elements, the waveguide below it heats up, thus changing the refractive index very little, and you can either switch the signal or change the properties of the signal based on the heat. So, typically this is used for on off switching, is one of the important applications, and you can also create variable output power based on the heat that you apply to this. So, this is shown as an example. You have a titanium film heater, the substrate is a soda lime glass, and the device is fabricated on proton exchange waveguides or potassium ion exchange waveguides. One of the important disadvantages you can say for such devices is the speed, because of the heat involved, and the processes is quite slow compared to other electro-optic effect or other devices. So, we have already seen electro-optic devices as an example. I am showing you the electro-optic devices where you have electrodes that can be used to manipulate the light that is propagating inside the waveguides. On the right side we see a device which can be used for a high speed of modulation. Typically the electrodes will form coplanar structure. In the microwave terminology you call them coplanar waveguides, and a microwave signal is distributed across them, and there is a variable voltage that varies along the length of the waveguides also exists, and the light that is propagating below these microwave waveguides is affected by the microwave that is impressed upon the electrodes. So, this is a good example of high speed operation. Typically microwaves are of the orders of gigahertz and light waves are of the orders of terahertz. You can say that these are the electric waves are almost stationary compared to the light that is propagating, but there is interaction between the microwave and light wave leading to a very high speed operation. So, typically these are made on the lithium niobate is a very good electro-optic material, and you need a lot of other engineering like the matching of the electrodes, then the proper alignment of the electrode with the optical waveguide, and so on and so forth. So, this is another example of electro-optic switches that we have already seen. There are a lot of configurations that we can think of. Typically I would like to highlight on the second portion where there is a delta beta coupler. You can choose the voltages across these couplers to change the properties and tune according to the requirement, and you can also compensate for the fabrication tolerances and the minor electrical voltage variations and get a very stable modulated output voltage by such a configurations. So, acousto-optic effect essentially implies that you can change the properties of the medium by a stress wave. Here what is shown is called an interdigitated transducer, which is highlighted below. There is an alternating positive and negative electrodes shown and a waveguide below, and when you apply an RF signal to these electrodes, it is possible to create a stress wave on the crystal. So, here it is shown that a stress wave is created in this direction, and the refractive index is a function of the stress wave. So, as you know, as the stress wave is a periodic variation, you can think of periodic variation of the refractive index, thus creating a grating. So, if you create a grating by this acousto-optic effect, the incident light could be deflected into any direction that is desired. So, these acousto-optic devices could be used as a very well as a deflectors and in many other applications. So, the magneto-optic devices are effectively based on the magnetic properties of the material, magneto-optical properties. You can create a refractive index change or the other changes in the anisotropy of the materials by using the magnetic effects. So, typically we need magnetic materials like garnets, like yttrium aluminum garnet, yttrium iron garnet and so on, and you can have special electrodes to magnetize the material and create magnetic effects on that. Typically a term that is used is surface waves on the crystal. Magnetostatic surface waves are created by using these magnetic effects at variable frequencies, and these can be used for many applications like mode conversion, then polarization control and so on and so forth. So, just a brief mention about the nonlinear effects, which we can go into detail later on. Nonlinear effects effectively imply the properties of the medium are dependent on the light that is propagating inside these crystals. Delta n is a function of the electric field of the light wave. So, you can expect for a particular intensity of the light, for example for a intensity of the light less than some threshold value, the light in the waveguide could be a linear, could be operating linearly where light will propagate just inside the waveguide, whereas if the intensity of the light crosses a threshold, you can say that it can deflect or leak out into the substrate. In particular, there is what is called the second harmonic generation. From a given light wave of a certain frequency, you can create harmonics of that, creating light waves at different frequencies, for example the double the frequency and so on and so forth. That is what is shown here. Once again, typically the lithium niobate is a crystal which has got many of these interesting properties. So, here what is shown is the input wave light at 840 nanometers, creating a second harmonic at 420 nanometers. So, let us look at some fiber optic systems using integrated optics and the applications of how these integrated optical devices could be used in these applications. We look at 3 examples, one for communications, one for a sensing application and an information processing application and so on. This is a typical fiber optic communication, very simple fiber optic communication link, where at a particular given node in a network you need to switch between different output ports. Let us assume there are 4 nodes to be addressed and each one operating with a different signal. So, all the signals could be addressed through optical fibers. There are 4 input ports S1, S2, S3 and S4, or X1, X2, X3 and X4, because and the requirement is that the signal has to be routed into any of the output ports Y1, Y2, Y3, Y4. So, the specification is given in terms of a transmission matrix, for example X1 going to Y4 and X4 going to Y1 and so on and so forth. So, as you know, the operation of an optical switch, for example the first switch could be in a crossover state or bar state. Each of these switches could be programmed to be in any of those states, and it is possible to program these such that you get the desired connectivity. For example, if you put S1, S2, S3 all in crossover state, we can expect that X1 will go to the last port, and similarly if you put the S3 and S4 also in the crossover state, you can also expect simultaneously X4 to go into port Y1. You can easily work out that all combinations are not possible, and you can think of higher configurations where you use more switches to achieve the desired connectivity. So, this is a typical 4x4 switch array that is useful for fiber optic communication systems. So, this is an example of an optical information processing system, a typical example of an spectrum analyzer. What you see is a chip of lithium niobate you have a slab waveguide onto which two lenses are impressed upon it. These are called geodesic lenses created by creating a stress impressed upon those regions. So, you have a laser diode as an input, and you have a photodetector array to capture all the scattered signal, and this you have an acousto-optic transducer here which will create a grating sound wave in between and inducing a grating, and this grating is the one which will deflect the signals across different output ports. The input port is input lens is used to spread the signal across these grating, and the output lens is used to deflect the focus the deflected light across different photodetector array elements. So, if I give an RF signal at the acousto-optic cell, so the created grating follows the frequency of this RF signal and the deflection corresponds to those frequencies. If there is a composite signal here at the IDT or the acousto-optic cell, then there is a composite grating here, and the output signals at the photodetector array can correspond to the distribution of the microwave RF signal at this input port. So, you can say that this can act as a RF spectrum analyzer. It is also possible to configure this as an optical spectrum analyzer by giving a constant frequency to the input signal and a variable input light spectrum. So, you can configure this such that the output corresponds to various components of the input light spectrum. So, you can configure this device as a RF spectrum analyzer or an optical spectrum analyzer. One more example of integrated optical device of circuits is for a fiber optic gyroscope chip is a sensor application. A fiber optic gyroscope typically has a coil of fiber, several rounds, and the basic principle of operation is based on the Sagnac effect, where you have the light passing through this coil in the clockwise direction and anti-clockwise direction. So, the phase difference between the clockwise and anti-clockwise propagating waves is proportional to the angular velocity of the entire object onto which this gyroscope is placed. So, in order to function, in order for this device to function, the gyroscope to function, you need several components, like you need to split the light between the input and output ports, you need to have a polarizing devices because all the devices, all these operate on the single mode operation, then so that you need a polarizer to be created on the chip. Then we need a modulator so that the biasing point of this phase can be shifted and so on. It is apparent, it is pertinent to make note of various components that are necessary for a fiber optic gyroscope chip. So, an integrated optical approach provides a very compact solution to create all these components on a small chip. Of course, there will be a lot of other electronics involved for detection and for processing and display of the signals and so on and so forth. So, what I mean to say in the as an application is that several components necessary for many applications like the sensor could be fabricated on a single chip. So, this is a final example called a disk pickup device, quite popular some time ago. So, it has got the main application is there is a optical disc here which is very finely controlled, or the granular sizes are very finely controlled, and the requirement is, the optical requirement is that each of these have to be addressed very finely, so that you can have a high density storage. So, a focusing grating lens is used here to read and write the signal. So, such devices could also be fabricated on a small chip, and the whole entire system could be very compact by the use of integrated optical devices. Of course, a lot of electronics is needed for processing these signals. Finally, it could be said that integrated optics is a very interesting and very useful subject in the modern optics and many applications to optical communications, sensors and so on and so forth. We can say that all optical operations are one of the important direction in which the integrated optical circuits are moving towards. There are several current literature available in practice, and I have shown a few of these, and I hope the course will be very interesting to you. Thank you very much.